Hello everyone! This is the first of a series of videos dedicated to the use of chromatography in the context of environmental measurements. We are going to be looking at the scientific basis of chromatographic techniques, and we'll also be looking specifically at some types of chromatography: thin layer chromatography, TLC, high performance liquid chromatography, HPLC, and gas chromatography, GC, and specifically gas chromatography coupled with an spectrometric technique called mass spectrometry. This video will be split into several sections just to make it easier to follow. So what is chromatography? Well, chromatography is a generic term that we use to describe a series of methods to separate mixtures into their individual components. And they can be from separating color substance in a particular absorbent material, or to using a piece of equipment to do a separation of a mixture. But in all cases, it is about a mixture which is separated in individual components. It was discovered in the early 20th century by a botanist, a Russian botanist, and the first component to be separated using chromatography was plant pigments, specifically chlorophyll. He used ether as a solvent and used a piece of paper to separate the different types of chlorophyll. And it was not until the 30s that the technique moved from paper to a more common type of chromatography we use today, which is thin layer chromatography using silica on a supported system. The name comes from chromos, which means color, and graph, which means drawing. So it literally means in Greek something like color drawing. Svet, the original botanist that came up with the idea of chromatography, defined chromatography as a method in which the components of a mixture are separated on an adsorbent column in a flowing system. And this is very much what chromatography is. So you've got here a picture or a schematic representation of how paper chromatography or thin layer chromatography will look like. You have a series of spots from 3 different chemicals. You don't know if they are mixtures or individual components. You just have that you have them spotted in a piece of paper, for example. That piece of paper is put in contact with a solvent and in an enclosed chamber, and the solvent goes up the piece of paper through a capillary process. So the different substances have different affinity for the solvent and for the paper. Those that have more affinity for the solvent will travel further up the paper. And those that have less affinity for the solvent, they have more affinity for the paper, will travel slower. So when the experiment finishes, when you take that paper out, they will have been left behind. So for example, after this particular experiment is performed, you have here an idea of how that may look like. We can see that the first spot, it was actually a mixture of 2 compounds, the orange and the red one, and they haven't been properly separated, but you can see that there are 2 chemicals in that particular spot. The one in the middle is the one that has got more clear separation, and you can see that actually that initial purple spot is a mixture of 3 different compounds. And then the final spot, you can see that it seemed to be an individual component. There didn't seem to be any mixtures, any additional components in this particular spot. Or if there are, whichever solvent we have used has not been enough to split them, to separate them in individual chemicals. All chromatographic techniques are based on the way a chemical or a mixture of chemicals will distribute themselves, will separate themselves between 2 phases. the mobile phase, in this case the solvent, and the stationary phase, that in this case is the paper. So again, as I was saying before, all chromatography is based on the same principle, the partitioning of a substance or a mixture of substances between two phases, and the preference of each substance for one or the other. One of the phases, we call that the mobile phase, and that is the one that is literally going to be moving. It will be a solvent, a gas or a liquid, that will pass over the second phase. And we call that second phase the stationary phase because it's the one that doesn't move. And so the mobile phase can be a gas or a liquid or a mixture of liquids. And it will be the one that does the separation. And the stationary phase can be a solid, or it can be a liquid supported on a solid, or it could be a solid or a liquid supported on a solid contained in a column. The way the stationary phase is packaged, depending on the type of chromatography. But you have the mobile phase and the stationary phase. Your mixture, the components of your mixture, will interact differently with the mobile phase and the stationary phase. Some of them will be more attracted to the stationary phase and they will travel further, or they might not move at all. Others will have more affinity, more chemical affinity with the mobile phase, structural affinity with the mobile phase, and they will move with the mobile phase. They will move faster or further along. They will move at different speeds, and those substances that were initially as a mixture will be separated as they pass down a column, if you have your stationary phase on a column, or a piece of paper if your stationary phase is a piece of paper, or a thin layer of aluminum or silicon oxide supported in plastic if you're using thin layers chromatography. This separation between the mobile phase and the stationary phase and the partitioning of that substance is based on something that we have discussed in other videos for this module, which is the partition coefficient, how that each substance will partition differently between the mobile phase and the stationary phase. So the partition coefficient, as we have described before in other videos, describes the behavior of a particular compound when it partitions between two different phases. And in this case, we have the stationary phase and the mobile phase. A compound that has a large partition coefficient means that it interacts more strongly with the stationary phase. It will take longer for that compound to leave the stationary phase because it will feel less attracted to the mobile phase, so it will not be dragged along by the mobile phase. That will lead to what we call a longer retention time, which means it will take it longer to leave the stationary phase. Retention time has a particular definition that comes from column chromatography, and we will look at it later, and it will make more sense when I show you a graph. At the moment, suffice to say that retention time is defined as the time that it takes for a particular compound from the moment it touches the stationary phase to the moment it leaves the stationary phase, which is packed in a column. If you keep all the conditions the same temperature, the same flow rate for the mobile phase, the same type of mobile phase, the retention time is characteristic of the compound. So a particular compound, because of its structure, will be attracted to the stationary phase in a particular way. And when a mobile phase is a particular mobile phase is applied, it will interact with the stationary and the mobile phase in a particular way. And as long as you keep the conditions constant, the speed in which the mobile phase is flowing through the stationary phase, the type of stationary and mobile phase, temperature and pressure conditions, if you can control them in that particular experiment, that speed, that retention time, that time it takes for the compound to move through the stationary phase is characteristic of what that compound is. So it can be used to identify, separate compounds, but also to identify them. So this is an example of column chromatography. The previous example I was showing you are typically how paper chromatography looks like. It was the first chromatographic technique that was invented. So in this case, your stationary phase is not a piece of paper, is a solid or a liquid absorbed in particles of solid packed in a column. It could be a glass column if you're doing column chromatography, and we will see that for HPLC and TLC, that stationary phase is packed in a metallic column. You've got your mixture, which is, in this case, it has 3 components, and these all together, and that's what this peak is trying to show. You flow the mobile phase throughout your column, and the different components of your sample, of your mixture, interact differently with the mobile phase, and they will be more or less attracted to the mobile phase. The one that is more attracted to the mobile phase, that is more chemically, physically similar to the mobile phase, will travel further and faster than the ones that are less attracted to the mobile phase. And then you start getting a separation. You don't have one mixture anymore. You start seeing this separation of the 3 different components. And if your column is long enough, you get a good separation between the components of your mixture. So at the end of that chromatographic process, when the chemicals leave the column, they will leave it, they were put in the column, they were injected in the column all together in a mixture. They will leave the column as 3 different substances individually. They will have separated.